Okay, let me say a little bit about this problem 9.4.8.
This is actually not
It
something
talks about
new.
the set H.
We've seen it before, but we're going to look at it from a slightly different
that is
perspective.
Hn equals the
And we'll find that
set
that's
of complex
valuable
numbers
to
such that you
explain
raise those numbers
groups
to the
of
nth power
symmetries and
get one.
motions
So part A is
of
prove
familiar
that Hn
objects
is a
like
subset
polyhedra.
of
The focus
T,
on this chapter will
and
be
remember that
especially
T
on
is
polyhedra.
the
Now,
unit
previously
circle.
we looked at the dihedral groups, which were motions of polygons.
Now, what is the unit circle? Unit
Now we're
circle
going
is
one
the
step
set
up,
of
and we're going to look at
complex
motion
number
of
z such
polyhedra.
that z equals 1.
Before we get there, let's give some basic definitions.
I'm writing
Now,
this sort of
when we
informally,
talked
but I
about the
just want you
dihedral
to
group
see what it
D6,
means. It's the unit circle in the
we
complex
considered
point.
these
All right,
group
so
elements as
what does Hn
permutations
look like?
of the
Now, if you go back
vertices
to
of a
proposition
hexagon.
2.4.12,
Since the hexagon has 6
we find out
vertices,
that the nth
we
roots
could
of
label
unity in
those
polar
A, B,
form
C,
look
D,
like
E,
this.
F. So
And
you may
there are n
imagine
of
in your
them,
mind a hexagon
because
with
K
the
can
vertices
take
labeled A, B,
values from
C,
0 to n
D,
minus
E, F.
1. So
And
if I
go
want
ahead
to
and
write
label them
Hn explicitly,
counterclockwise.
Hn is going to be the set.
C, D,
Well, I need to
E,
replace
F.
K as
So
0
around
to
in
n
a circle
minus
this
1,
way.
1 by 1 in this expression.
Now, if we wanted to
So the
rotate the
first one is going to
hexagon
be cis of 0,
counterclockwise
second
60
one is going to be
degrees, the A
cis
would go to B, the
of
B would go to C,
2
and so
times
on.
1 times
we could
pi
express
over
that
n. Third one is going to be
rotation
cis
in this tableau
of
form. This is
2
something we
times
saw
pi,
before in
2
chapter
times 2
7.
times pi, so that's 4 pi over
But notice
n.
what's going on here. The
And then
rotation is a function
and the
that
last one
acts
is
on
cis
a
of
set.
2
The set is
times
the
n minus
hexagon, which
1
is represented
times
by
pi
the 6
over n.
vertices.
Okay.
And the rotation
that's
is a
my
mapping that
set
maps
of
these
n
6
numbers.
vertices to 6
Notice that there is an n
6 new
denominator.
vertices.
Many people left that off.
Right, so really we have two things going on.
The question
we have a
is
rotation
Hn a
and we
subset
have a
of
set.
T?
And the rotation acts on the set.
Well,
So
T
here
is
we
the
did
set
this
of
for
numbers,
D6
complex
hexagon.
numbers whose absolute
Of course,
value
we
is
could
1.
do that for
So all I
any
need to do is
n-gon.
show that the
So
absolute
that's what this
value
exercise
of
is
each one
asking
of these
for,
is
to
1.
generalize to an
And
n-gon.
notice that the
But
absolute
now
value
let's take that
of
idea and
cis
generalize to any
of
set.
2k pi.
Okay, again, I
over
mentioned
n.
that here when we have this set
Well,
up
rewrite
with
this as 1
rotations
times
of a
cis 2
hexagon,
pi,
you have the
k
set
pi over
which
n. Now, if you
consists
remember
of the vertices,
from the polar
and you have the
form, this is
motion
the
which consists
modulus,
of a rotation.
and then this is the
Now the
argument.
group elements are
Now,
the
the
rotations.
absolute
rotations
value
move
of
the
a
set
complex
around, but the
number in
group
polar
elements are
form
the
is just its
rotations.
modulus.
So in this setup, we have a set and a group.
So what does that
And
mean?
the
That
group
means all
acts
of
on
these
the set
numbers
X. Now the
have
general
absolute
properties
value
of a
1.
group action are listed
So they're
as
all in T.
follows. There,
So
a
all
group action
elements
on a set X is
of
a map
Cn
from G cross X
of
to X.
Hn
What that means is
are in
that
T.
we have a group element and the set X, and that gives
All right,
us
so that's part A. Now part B,
mapping
using proposition 9.4.5,
to another
prove that
group
H
element.
is a subgroup of T.
So this
All right, so
GX represents
9.4.5,
group
what
element
this says, you have
and
to show,
set
first of
point
all, that H has
maps
the
to
identity.
another point of the set. So that's what we've had here.
Then you
This
need to
group
show that
element
H
R60
is
and every
closed
point X of the set gives
under
us
the
a
operation,
different point of the set
in the group
corresponding to
operation,
each point X.
and then
That's
you
what
need
we
to
have
show that
here.
H is closed under inverse.
Right. Now, if we have the identity rotation, that's going to take this X to itself.
So let's see how
that's
we're going to do
expressed
that.
this way. EX is
So
equal
let's
to X.
look at this one by one. So we have H
Right,
here.
the resulting
so the
X
three things
here
we need
is
to
going
show:
to
H
be
has the identity,
the
H is
same
closed
if the
under
group
the
element
group
is the
operation, and
identity.
H is closed under inverse.
Now,
All
suppose
right, so first
we
of
take
all,
the
let's
composition
see.
of
First
two
part,
rotations.
We say that
well, we know that if we compose two rotations, that's the same thing as taking one rotation
in
after
H,
the other. And so that's expressed this way. G1, G2x,
since
that would be
the
putting
first
G1
element
and G2
here,
in here instead of G,
is equal to 1.
That's the same thing as finding G2x and then taking G1 of the result.
Okay, so 1 is in H.
So this should make sense in terms of your intuition of rotations.
And
this expresses the fact that you can do rotations one after the other.
And saying we need to show that it's closed under the operation. So we'll suppose
now,
if I have
this is something that you've seen in other classes as
so let's just do it a little more formally.
In linear algebra, for example. If you have a matrix, so let's specify specifically the group of invertible 2x2 matrices, which is a group. Now these act on vectors. We know that we can multiply matrices by a vector and get another
Z and W
vector.
have this form. Okay, so I can write Z
and if we
as
have
cis
two matrices, we multiply them one after the other and get the result acting on the vector.
And I can write W
So these follow the very same rules.
Of 2 pi.
You can multiply the two matrices together and act that on the vector.
So what is,
or you can multiply the vector by the first matrix and multiply by the result by the second matrix, and we get the same result. So this expresses the same ideas of group
2 pi k over
and this
n
exercise shows that we can also apply group action to other examples that we've seen before.
So that's equal to, if you remember how cis is multiplied, the arguments add, so I have cis of 2 pi k plus L over n. Now, the question is, this looks pretty much like it's in Hn, but the question is, you don't know that k plus L is in the range from 0 to n minus 1. But it doesn't matter, because if I take k plus L mod n, then that's not going to change the result of the cis. Why? Because if I add any multiple of n here to this k plus L, that's just going to give me an n on the top that cancels the n on the bottom. That's just going to be a multiple of 2 pi. Since it's a multiple of 2 pi, that doesn't change the cis. Okay, so that's equal to, I could write that equal this way, it's equal to cis of 2 pi, and then that's times the mod of k plus L mod n divided by n. So that is in Hn, because mod k plus L mod n is in 0 to n minus 1. Sorry. All right, so let's do the last one, closed under inverse. So here I can say closed under the group operation. Okay, last one, closed under inverse. Well, let's take Z, element Hn. That implies that Z is equal to a cis of 2 pi k over n. Okay, now let's consider what is the inverse of Z. Well, if you go back to the polar form, so Z inverse is equal to cis of, you can write it two ways. You can write it as cis of minus 2 pi k over n, or you can write it as cis of 2 pi times n minus k over n. Okay, so we can split this up into two cases. We can consider the case where k equals 0, or the case where k equals 0, that means Z is equal to 1. Because cis of 0 is 0. So Z inverse is in 1, and that's also in Hn. All right. Now, the other case is when k is greater than 1. If k is greater than 1, we also know that k is between 1 and it's less than or equal to n minus 1 by the description up here of the elements of Hn. The elements of Hn have k from 0 to n minus 1. All right, so we know that k is between 1 and n minus 1. In that case, I know that n minus k, well, what's the biggest n minus k can be? Biggest it can be is n minus 1. I'm sorry, this should be k greater than or equal to 1, sorry. So the biggest this can be n minus 1. That happens when k is equal to 1. What's the smallest it can be? Well, the smallest it can be is when k is equal to n minus 1, and that's going to be 1. Okay, so n minus k is between 1 and n minus 1. So that means that cis of 2 pi n minus k over n, then this element here, according to my specification of Hn, since n minus k is between 0 and n minus 1, it fits the specification that's given here. Right? I have an n minus k. I'm just replacing the k with an n minus k, but that n minus k meets this condition. So that means that this element here is in fact in, where's my mouse? Okay, is in fact in Hn. Okay, so it's closed under inverse. Okay, and that's it.